Welcome to the third week of the Digital Circuits and Systems unit. This week we're going to talk about binary code and two's completement. In particular, in this asynchronous session video, we will talk about two's completement, and we will also show the addition and subtraction of signed and unsigned binary numbers. So let's talk about negative numbers in the binary system. In the decimal numbering system, we use what is called a signed magnitude system. This means that we use a symbol for the sign and a number that represents the magnitude. Moreover, if we omit the sign, this means that we talk about a positive number. For instance, plus 98, if you see it as simply 98, you know that it's a plus 98. Now, when it comes to binary numbers, we don't have signs. What we do instead is that we use the first bit, the most significant bit, to indicate the sign. For positive numbers, this means that the most significant bit is equal to 0, whereas for negative numbers, the most significant bit is equal to 1. These are some simple examples of positive numbers in the binary system and their counterparts in the decimal system. And these are the negation of these numbers. As you can see, we simply flipped the bit from 0 to 1, and that indicates a minus sign in the decimal numbering system. Now let us check out this example over here. You see a series of decimal numbers from -7 up to 7, and then you see how we represent them in the binary system using a signed magnitude. So a signed magnitude system has an equal number of positive and negative integers. In this example over here, please ignore -8 and focus on what we got over here. From -7 up to -1, you got in total 7 integers. And at the same time, you've got 7 positive numbers from 1 up to 7. Now, what is important to note is that when you use a signed magnitude system, then you have two representations from 0, which makes sense. It's like saying -0 or +0. It means exactly the same thing. In general, if you have an n-bit signed magnitude binary number, I will let you think about it and come up with the right answer. What is the range within which this number lies? If you paused the video and took a look at this example, you would have realized that this is the general answer. So in our case, we have 4 bits, which means that our numbers lie between -7 and 7. Finding the opposite of a number, which is called the act of negation, consists of just changing the sign bit. This is very simple. Now, in order to perform an addition or a subtraction with signed magnitude binary numbers, things are easy. If you're dealing with two numbers that have the same sign, you just add the magnitudes and then use the same sign, regardless of positive or negative. Now, there is a little bit of more work to do if you're dealing with numbers with an opposite sign. In this case, you need to compare the magnitudes, and then you subtract the smaller one from the larger magnitude. At the end, the result takes the sign of the larger number. Let me correct that, of the larger magnitude. In subtraction, you change the sign of the number to subtract and proceed with an addition. Now, this is something that we need to take a more close look at. So when we're dealing with additions with the same sign, the result may exceed the n bits that you have available. This is something which can happen, and you can easily detect it because a carry will occur out of the most significant bit. Now let's talk about binary radix complement systems. And more specifically, let's talk about the 2's complement. Now, as you have probably realized by now, the sign magnitude systems, arithmetics, suffer from complexity, which means that it's not a system that you can implement efficiently. So this is why we use what we call 2's complement. Now, 2's complement numbers, which are added here next to the sign magnitude system numbers, as you can see, again we use the most significant bit to indicate that a number is either negative or positive. And this is what we do. In order to find the decimal equivalent of a 2's complement binary number, we compute the same way as for the assigned binary numbers, as you can see over here in this part. And then we use the most significant bit with a weight that is equal to -2 in the power of n minus 1. Now, this has implications. As you can see, compared to the signed magnitude system that had 2 representations for 0, here we use only 1 representation for 0 and an extra one for the negative numbers, which increases the range from -7 that it used to be before to -8. So overall we got one more number for the negative numbers to represent, which changes what we previously shown to a range within -2 in the power of n minus 1 up to 2 in the power of n minus 1 minus 1. And we also note that this extra negative number, it has no positive counterpart. Now, I'm sure that most of you by now would be thinking why we call it 2's complement. Well, there's an explanation for that. If you go to this table and you take any number from it, and then you also take its negation, well, if you add them, and then you start adding each pair of bits, you will realize that the result is always 2. Which gives, of course, a 0 as a result and an ignored carry. Now here we got two simple examples. If you try to add 3 and -3, 1 plus 1 gives you 0 plus a carry. Then the carry plus 1 plus 0 gives you 0 again plus a carry. Then 1 plus 0 plus the carry gives you again 0 plus a carry. 1 plus 1 gives you a 0 plus a carry that you're going to ignore. So this is why it's called 2's complement. And this is another example. You can go through that example as well. Now let's build a 3 bits 2's complement number system. So what is the minimum representable decimal value? Well, based on what we said, it's -4. And what is the maximum representable decimal value? Again, based on what we said, that is 3. Now here are some nice properties. We start from a number that is essentially starting with 1 followed by zeros. We simply need to change the most significant bit of 0, 0, 0 to 1. Remember that we're using a 3-bit system. Another nice property is that for any consequent number, the only thing you need to do is just add 1. So if you go to -4, which is 1, 0, 0, you just simply add 1, and then you got -3. Then again you add 1 and you get -2 in this form, and so forth. We say that there is no complement from 0, 0, 0 because obviously that is used for -4. And there is a similar way for the assigned binaries. You start from 0 and you keep adding 1 each and every time. Now this is a nice property. Turning into this slide, essentially it says the same thing. If you notice at the slide, you will find out that the basic property that we get from 2's complement is that adding becomes an extension of just counting. In order to go from one number to the next, you simply need to add 1. Now here are some simple examples of a 4-bit 2's complement addition. Let's start with 3 plus 4. We expect that the result would be 7. As you can see, by adding the numbers, it's very simple. 1 plus 0 gives 1, 0 plus 1 gives 1 again, 1 plus 0 gives 1 again, and 0 plus 0 gives 0. Now, based on the tables that we've shown earlier, this is equal to 7. Now, let's check out what happens when you try to add two negative numbers, -2 and -6. In this case, what happens is that 0 plus 0 gives 0, 1 plus 1 gives 0 plus a carry, 1 plus 0 plus the carry gives 0 and another carry, 1 plus 1 gives 0 and another carry. And that is ignored. And this is the representation of -8. This is another example when we try to add a positive and a negative number. The expected result should be -3 here. If you go through this example, it's quite simple. You will see that the result is again -3. Just remember from these examples that you always need to ignore the carry beyond the most significant bit. So obviously, adding two numbers becomes a very easy process. Moreover, this process is very straightforward and also includes adding two negative numbers to one another and subtraction by converting it into an addition between a positive number and a 2's complement representation of a negative number. Now let us talk about the special case of an overflow. An overflow happens when the result is out of range. It is worth saying that one of the nice properties of 2's complement is that the addition with two numbers with opposite signs can never give a result out of range. An overflow can happen only when you're adding numbers with the same sign. And this is one example. Here we try to add 3 and 6, and the expected results should be 9, but instead you get something which is mapped to -7. Now again, if we try to add -3 and -6, although the expected result would have been -9, you get something which is interpreted as 7. As we previously said, both examples have one thing in common, and that is that the numbers we try to add have exactly the same sign. In this example, a positive sign. In this example, a negative sign. So that can be easily detected if the result has a sign which is different than the sign of the two numbers you're trying to add. So overflows are easy to find with 2's complement. Now let's see what happens when you try to do subtraction. The subtraction is a very easy process with 2's complement. What you need to do is simply take the number you want to subtract, in our example that is -6, and negate it. The process of negating a number in 2's complement is very easy. You just take the bits as they are here. Now, we found these bits from this table. You just flip each and every bit, and then you add 1. So, as you can see, the process of doing a subtraction with 2's complement is as easy as just a simple addition. The only thing you need to do is take the second number, the number that you want to subtract, flip all the bits, and then when you try to do the addition, remember to add 1. Now, if you go through this example one by one, you'll find out that the results are easy to find. 1 plus 1 gives you a 0 and a carry, but then you add 1 as well, so that 0 is converted to 1. Then you had a carry before that, so 1 plus 0 gives you a 1 over here. So 1 plus 1 and no carry gives a 0 plus a carry. 1 plus 0 plus the carry gives you a 0 plus a carry that you are going to neglect. So 0, 0, 1, 1, based on this table over here, is 3, which is the expected result. And with that, we've reached to what is the final slide of this asynchronous video. At this point, you can hit the pause button and go through the summary with everything that we said. But besides this, there are a few extras. For those interested, you might be wondering why we have a 2's complement. Is there any 1's complement? The answer is yes. And by using this QR code here, you can go to a nice video on YouTube and learn more. 1's complement is so easy, you just need to negate each and every bit. So you simply flip the bits. As you can understand, it's a very easy process, it doesn't cost much. However, we don't use it, and there's a good reason for that. Let's see that reason through an example. Let's say that you try to add 5 and minus 5, or in general, x and minus x. The result that you're going to get is 1, 1, 1, 1, which is used for 0. Okay, so this means that you need to use this representation for 0, which doesn't look nice. But that's not the real reason why we don't use 1's complement. The real reason can be seen in this example. Suppose that you try to add 5 to minus 3. Well, if you convert them to 1's complement, which, if you remember, is as easy as flipping all the bits of negative numbers. So normally 3 would have been 0, 0, 1, 1. So by flipping the bits, you see that the result in 1's complement is 1, 1, 0, 0. If you add those two numbers, the result is going to be 0, 0, 0, 1 and an ignored carry. However, this result is not what we want, because this is interpreted as 1 in the decimal system and in the binary system, which is wrong, because you would have been expecting to get a 2 as a result from adding minus 3 to 5. So in general, 1's complement is one number off. And this is why we don't use it. Now, if you are interested into watching a different tutorial online that summarizes everything in a very practical video, for 1's complement and 2's complement, you can visit this URL over here or simply scan this QR code. Let me note that those extra slides are not part of your material. It's just for your own information and just to trigger your curiosity.